Yes, by the time you finish reading the entire title, my presentation might be already over. So I'm trying to sum it up, what we actually done in this year of my PhD. Basically, we try to find a way to define the uncertainty for densities for satellites, because overall, that's what link basically with risk assessment. I want to thank first my supervisor, Professor Peter Brown, Denis Vida, and our summer student, Emma Harmus, that help us out with some of the reduction. So, I guess most of you now know quite well this meteor, I hope. Yesterday, quite a few of us talk about this, Neres and the others. Stunning visual, not mine. It's a ugly GIF that I find online. But still, just to point out that these events are very rare, especially when we talk about like one of these very big fireballs events. And most of the one that we are kind of talking about when we talk about risk assessments are often very small. Those pesky tiny pebble size objects that impact to our satellites up there kind of make a lot of issues up there. So over here you see something that also Joachim and also Peter already mentioned. There is a range where we start having a few issues, and at some point there's not that many to worry about it, basically. So overall, this is the range of meteors that we're trying to look at with our cameras. And when we talk about risk assessment, there are just two variables that we're dealing with mainly: the velocity at which these meteors are traveling and the density that they have. Very easy, like as of course we have from one side we can define this. Of course, I didn't mention this, but this is also Emma pointing out the same graph. And of course, the denser and faster it is, the worse is the damage to the satellite. It doesn't take a genius to get that. But overall, what I want to point out here is just that the uncertainty range that we can manage to get at this point with CAMO, it's in the order of tens of meters a second, which is especially impressive considering that these things travels at tens of kilometers a second. The problem stands for the density here. The density is quite hard to estimate, the uncertainty with that. We need a model. The one that we use is the Borovitchka model 2007. Thanks again, you did great. It's very useful. We continually use this model and it seems to be working fine. The only problem with this, Jerry, it's that it has a lot of variables and we need to tune them all. And of course we need them because we want to have a good fit for our single calibration. The problem is that it takes a while. So this is where we start thinking about trying to automatize this method. Overall, just to point out here, we have here this is the MetSim interface that we have, a WMPG GitLab repository that you can also freely download here. The thing here is the two camera that you see over here, and the one, the simulated one, is the one that we have a manual fit that we have done. The problem stands when we try to do an automatized way to figure out which might be the actual physical properties of these meteors. So we try different machine learning technique, but none of them seem to be working fine. So we resulted in a different method that I'm going to introduce you. But overall, we have a ton of observed properties that we know quite well, also in the uncertainty-wise. Here we have the velocity, the magnitude, the duration, the zenith angle, and the height, but we have also quite a lot of other. We have 20 more of them when we consider the actual program that we run. And on the other side, we have the physical properties of the erosion-fragmentation model. So we have the density here in red, and the mass, and the ablation coefficient, and the erosion coefficient overall. What we do, easy. We just have an observe event. We just want to make sure we generate a ton of simulation in order to get a few that are quite close to the one. So here, here you see here basically the distribution of velocity. The green value is the observe event, and we sort of have this distribution for each single meteor that we have to get a solution with. What we applied here is the principal components analysis that help us out managing to create a new search space that maximizes the variance, and through this, we can just figure out the distance metric from the actual observed event to the other simulations over here. And this PCA, so principal components, each single one of them give us some sort of a distance that can be used to assess how different two simulations are between each other. Okay, so this is just another way of, and this basically after a certain threshold. So over here, then after that, we have the root mean squared difference from the deceleration and the magnitude. It's so much that we have to stop selecting the simulation overall. A easy way of putting this is just that we're trying to play darts with 1,000,000 darts. So we have our random simulation events with a different kind of physical range of parameters. We have a range of densities for the Perseids that range from 100 to 1,000 kilogram per meter cube, and we have a range of masses and so on, and we just throw them in at the dartboard and figure out which one of them is the closest to the real event. And we can tell that based on the PCA distance metric. And the root mean squared threshold actually tells us if we are at the dartboard or not. So this is just an easy way to point that out. But anyway, when we have these resulting fit, we can now extrapolate their physical properties because we simulate those, so we know everything about them. And with that, we can now get these resulting solutions. So over here you see the distribution in densities. And the one in black is my manual reduction. The dashed red line is the mode of this distribution. And over here you see the resulting curve fit that we ended up with. The green dots over here are the observed event. So in the end, what we gathered, we just use this model for a few of our meteors. Here we have like about a dozen or so meteors for each single one of them. We use that on the Perseids, the Uranids, and the Alpha Capricornids. We ended up making sure that this model actually worked with one single fragmentation event, which actually ended up working for some of them. For this reason, we didn't manage to make it for each single one meteor that we have. So for this reason, here you see the distribution for each single one of them. And this actually panned out well with all the other papers. And here we no longer use the sort of median value, but we use the mode that you saw over there and the uncertainty range that is the confidence interval that we estimate from the tens of meteors that we have data for. And overall, the idea behind it is to apply the same method to the sporadic meteoroids in order to figuring out their density distribution, as they have quite of a big difference in density, and we have both cometary material and asteroidal material, so we want to make sure we have quite a good grasp of it before we introduce our Monte Carlo model that I already pointed out the previous IMC, and we're trying to use in order to help out the NASA Meteor Engineering Model version 4, or at least we hope so, but that's all I have to say. Here is a brief summary of the presentation. And if you have any questions, feel free to do so.
Jerry.
Yes, very nice work. Thank you. My question is simple. Do you model also the wake or just the light curve and dynamics?
No, we don't model the wake. At this point, we just model the light curve and deceleration in this case.
Yeah, in that case, the solution may not be unique.
Yeah, exactly. And that's the point, right? Probably I didn't stretch it out enough. But the thing is, we did the manual reduction, but of course, there is a lot of degeneracy because we have a ton of other parameters that we can tune. So we can just change a little bit of density, and then we can change ablation coefficient, and we get another fit. So this is actually to address this, exactly. So we need to find multiple solutions for the same meteor because of this multitude of solutions that could be available with the number of parameters that we have to work with.
Mm-hmm. Thanks.
So, any other question or remark? I also don't see anything online.
Oh.
Yeah, okay. Sorry.
One question. Does the contribution from different parameters to the principal components change between the sources? Like, does the density matter more for a certain event compared to others?
Yeah, we are actually looking into that right now, and we see that there are definitely some that they are definitely more linked to each other than the others. And now I can't tell for sure, but like each single meteor that we look at, it's quite different from each other. Like they always have some sort of a different way of making it harder than expected. So every single one of them, it's special in their own way. Like, and so for this reason, we might have like the density, the ablation coefficient for one. The other one might have the grain density. So sorry, the grain density, the grain mass. The upper and lower might also be linked with the erosion coefficient. And all this is just to say that they change quite substantially, but meteor to meteor, and also the correlation between a parameter to the other.
All right. So,
Okay.
thank you very much. Let's
No
thank Max again.